Beyond the reach of our sun, a star flickers. Not the steady, reassuring glow we have come to expect from the countless suns that fill our night sky. Not the gentle twinkle caused by Earth's restless atmosphere. This is different. This is deeper. It is an irregular dimming, sudden and sharp, as if the very heart of the star is faltering. It is the kind of flicker that whispers something is wrong. For centuries, humanity has trusted the stars. We have looked up and seen them as fixed points in an otherwise changing world. The ancient Greeks traced them into constellations and gave them names. The Chinese recorded their alignments and mapped their motions. The Polynesians read them like a map, crossing oceans with nothing but starlight to guide them. Through centuries of war and peace, the rise and fall of empires, the stars have kept their promise. They have shone with steady light, constant and unchanging. Until one of them didn't. In 2015, buried in the vast archive of data collected by NASA's Kepler Space Telescope, a small team of scientists noticed something impossible. It was a star, modest in size, ordinary in color, sitting quietly in the constellation of Cygnus, about 1,470 light-years away. Its official name was cold and clinical, KIC 8462852. But soon it would earn another name, one that hinted at the mystery it carried. Astronomer Tabitha Boyajian would bring it to the world's attention, and the world would come to call it Tabby's star. At first, the star seemed unremarkable. It burned steadily, like millions of others cataloged by Kepler. But then, without warning, it dimmed, not by 1%, as a large planet might cause when it passes in front of its sun, not by 2 or even 3%, which would already be unusual. This dimming was 10%, then 15%. At its peak, 22% of the star's light simply vanished. For context, even the largest planet in our solar system, Jupiter, would only block about 1% of the sun's light if viewed from afar. Whatever was blocking Tabby's star was enormous, and it wasn't happening once in a predictable orbit. It was happening at irregular intervals, sometimes lasting days, sometimes weeks. The first assumption was a simple one. There must be an error in the data, a glitch in the telescope. Perhaps something in the software had misread the signal. But the more the scientists checked, the more certain they became. This was no mistake. The dimming was real. The star was hiding something. The mystery began to spread beyond the research team. Astronomers debated it. Space enthusiasts speculated. News outlets picked up the story, often with dramatic headlines. Some called it the strangest light curve ever recorded. Others, more daring, called it a possible sign of alien life. It was, after all, exactly the kind of anomaly that invites the most tantalizing of questions. What could possibly cause such massive, irregular dimming of a star's light? Some scientists suggested a vast cloud of dust passing in front of the star, scattering and absorbing the light. Others imagined a swarm of comets, perhaps disturbed from their orbits by a passing star, and now falling toward Tabby's star and leaving thick trails of ice and dust behind them. But there was a problem with both ideas. The patterns of dimming did not match what a dust cloud or comet swarm should produce. The timing was irregular, the amount of light lost varied wildly. Nature seemed to be breaking its own rules. And then came the idea that caught the public's imagination. What if the dimming was not natural at all? What if it was the work of an intelligent civilization, building on a scale we could barely comprehend? In the mid-20th century, the physicist Freeman Dyson had imagined a structure so vast it could surround a star, collecting nearly all of its energy. A Dyson sphere, or more realistically, a Dyson swarm, a collection of thousands or millions of solar collectors orbiting in formation. To a distant observer, such a structure would block a star's light in strange and irregular ways, much like the dimming we were seeing from Tabby's star. The alien megastructure hypothesis was, by any measure, a long shot. Most scientists treated it as a last resort, an explanation to be considered only after every natural possibility had been exhausted. But the moment it entered the conversation, The public could not let it go. The idea of detecting not just life, but a civilization advanced enough to reshape an entire solar system was too compelling to ignore. The search for extraterrestrial intelligence, better known as SETI, turned its radio antennas toward Tabby's star. If this was an alien civilization, perhaps they were transmitting signals. Weeks of listening yielded nothing but silence. Yet the absence of a signal proved nothing. A civilization capable of building on such a scale might communicate in ways we could not detect, or not communicate at all. And so the star remained a mystery, a puzzle, a challenge issued by the cosmos itself. For thousands of years, humans had looked up and believed that the universe was comprehensible, that its rules could be learned and predicted. But here was a star that refused to fit the pattern. Before we leap to conclusions, we must understand this. Stars do not behave like this, not without reason. And the rules they follow are not the rules of human preference or imagination. They are the laws of physics. Laws written long before the Earth existed and obeyed faithfully by billions upon billions of stars. To solve the mystery of Tabby's star, we must first understand those rules. We must know how stars are born, how they live, and how they die. We must learn what is normal so we can recognize what is not. This is the story of the star that should not exist. This is the journey from the heart of a cosmic enigma to the edge of human understanding. And as we begin, remember this: the universe is vast and it is ancient, but it is not without surprises. Somewhere in the darkness, a star is still flickering, still hiding its secret. And until we find the answer, we will keep watching. To understand why Tabby's star is so strange, we must first understand how stars are supposed to behave. A star is not just a point of light in the sky. It is a vast sphere of plasma held together by its own gravity, with nuclear fusion raging in its core. It is a delicate balance between two immense forces. Gravity pulls inward, trying to collapse the star, while the energy from fusion pushes outward, holding it up against that collapse. When those two forces are in perfect equilibrium, a star shines steadily for millions, even billions of years. Stars are born in cold, dark regions of space called molecular clouds. These are enormous, sprawling collections of dust and gas, sometimes dozens of light years across. Inside them, tiny ripples in density can grow under the influence of gravity, causing parts of the cloud to collapse. As the gas falls inward, it begins to spin and heat up. In the center of this collapsing mass, pressure builds until hydrogen atoms are forced so close together that they fuse into helium. When that first fusion reaction ignites, a star is born. For most of its life, a star exists in what astronomers call the main sequence. This is the long, stable phase where it steadily burns hydrogen into helium in its core. The exact characteristics of a star, its size, brightness, and temperature, are determined largely by its mass. The more massive the star, the hotter and brighter it burns, and the shorter its life will be. Small red dwarfs can burn for hundreds of billions of years. Massive blue giants may last only a few million years before exhausting their fuel. During this main sequence stage, stars are remarkably stable. They can have sunspots and small fluctuations, but their overall brightness remains constant to within a fraction of a percent. The rhythm of their light is so reliable that astronomers can detect the tiniest changes, such as the slight dimming caused by a planet passing in front of the star. This method, known as the transit method, is how the Kepler Space Telescope discovered thousands of exoplanets. When a planet transits the star, the drop in brightness is small and perfectly regular. The same amount of light is blocked each time, and the timing is exact. A planet like Earth, for example, would dim the sun by less than 1% for just a few hours, and it would do so every 365 days, like clockwork.
Even giant planets like Jupiter would only cause about a 1% drop in brightness, and they would do so on a predictable schedule. Nature provides other reasons for stars to dim, but these too are well understood. Binary star systems, where two stars orbit each other, can produce dips in brightness when one star passes in front of the other. Stars can also have variable brightness if they pulse or swell as part of their natural life cycle. But these changes are rhythmic, following patterns that can be modeled and predicted. The stability of stars is so fundamental that astronomers use them as cosmic yardsticks. By measuring their light, scientists can estimate distances, map the structure of our galaxy, and even determine the age of the universe. When a star's brightness changes in unexpected ways, it is like a clock suddenly skipping a beat. Something has gone wrong, or something entirely new is happening. Tabby's star is a glaring violation of these rules. Its dimming is irregular, unpredictable, and far larger than anything caused by planets or known stellar processes. It does not pulse like a variable star. It does not follow the rhythm of an eclipsing binary. It is not surrounded by enough dust to explain the light loss, and yet the light vanishes anyway. This is why the anomaly is so important. In science, anomalies are not just curiosities. They're opportunities. Every time nature defies our expectations, we have a chance to learn something new. Sometimes, as in the case of pulsars, the explanation turns out to be even stranger than the speculation. When pulsars were first discovered, their perfectly regular radio pulses led some astronomers to nickname them LGM, short for Little Green Men. The truth was no less extraordinary. Rapidly spinning neutron stars, the collapsed remnants of massive suns, sending out beams of radiation like cosmic lighthouses. Understanding how stars are supposed to behave gives us a framework for spotting the exceptions. The universe is vast, and while most stars follow the rules, a few do not. These rare rebels are the ones that push our science forward, forcing us to expand our models and rethink what is possible. When astronomers look at a star, they do not just see a light in the sky. They see the fingerprints of physics. The color of the light reveals its temperature. The patterns in its spectrum show us what elements it contains. Small shifts in that light tell us if it's moving towards us or away from us. Even tiny changes in brightness can reveal the presence of planets, moons, rings, or dust. This is the language of the stars, and for the most part, it is a language we can read fluently. But Tabby's star speaks in a dialect we do not understand. It dims deeply and without warning. Sometimes it recovers quickly, sometimes slowly. There is no pattern that holds for long. It is as if someone is playing with the light, drawing a curtain across it, then pulling it back, then doing it again at random intervals. This is not how stars behave, not in any stage of their life cycle, not in any known part of stellar physics. If there is a natural explanation, it is something we have never seen before. And if there isn't, then we may be looking at the first evidence of something truly extraordinary. But before we can explore the possible causes, we must understand the discovery itself. How did a small team of scientists find this anomaly in the middle of the largest data set in the history of astronomy? What exactly did they see, and how did they know it was real? The answer to that question will take us to the heart of modern astronomy, to the instruments, the methods, and the people who brought Tabby's star to the world's attention. And it will bring us to the moment when a strange light curve on a computer screen began to rewrite our understanding of the universe.
The year was 2009. NASA had just launched one of the most ambitious space observatories ever built, the Kepler Space Telescope. Its mission was as bold as it was precise: stare at a single patch of sky, unblinking, for years,
and catch the faintest dimming of starlight that might reveal planets orbiting faraway suns. Kepler's target was a tiny slice of the constellation Cygnus, the Swan, and a neighboring section of Lyra. In that small patch were over 150,000 stars, each one monitored continuously, each one recorded in exquisite detail. Kepler was not designed for beauty. Its images were not the dazzling photographs of Hubble. Kepler's power was in its patience and precision. It turned the universe into a spreadsheet, column after column of brightness measurements collected over time, forming light curves that told the hidden stories of distant worlds. This flood of data was far too vast for any single research team to comb through, so astronomers opened it to the public. They created a citizen science project called Planet Hunters, where volunteers from around the world could scan the light curves, looking for the telltale dip of a planet passing in front of its star. It was science powered by human curiosity, thousands of ordinary people becoming the eyes of discovery. Among the many stars in Kepler's dataset was one cataloged as KIC 8462852. It was an unremarkable F-type star, hotter and slightly larger than our Sun, about 1,480 light-years away. In photographs, it looked like any other point of light. On paper, it was just one more entry in Kepler's massive list. But in 2011, something unusual appeared in its data. A small group of planet hunters noticed that KIC 8462852's light curve didn't look like the smooth, periodic dimming of a planet transit. Instead, it showed strange, uneven drops, some shallow, some incredibly deep, and they were scattered irregularly over time. One dip was as small as 0.5%, another was 3%, and then there was one that plunged a staggering 15%. To put that in perspective, Jupiter passing in front of the Sun would just block about 1% of its light. For KIC 8462852 to dim by 15% meant something enormous, far larger than any known planet, was blocking part of its light. And whatever it was, it didn't come back on a neat, predictable schedule. The discovery caught the attention of astronomer Tabitha Boyajan, then a postdoctoral researcher at Yale University. She was part of the Planet Hunters science team and had been monitoring unusual finds from the project. When she saw the data for KIC 8462852, she knew immediately this was no ordinary signal. Planets simply don't do this. Even swarms of planets or moons couldn't produce such large and irregular drops in brightness. Boyajan and her colleagues began an intensive investigation. They combed through the raw Kepler data to rule out instrumental errors. They checked the telescope's calibration records. They compared the star's light curve with nearby stars observed at the same time to see if a glitch might explain the pattern. Everything came back clean. The dips were real. As the team dug deeper, the mystery grew. The most dramatic event occurred about 2 years into Kepler's mission, when the star dimmed by 15% for several days. Later, it would plunge by an incredible 22%. Nothing like this had ever been seen in the Kepler dataset. No other star showed such deep, erratic dips. It was as if KIC 8462852 had its own private eclipse machine, and it was operating without any regard for our understanding of orbital mechanics. The team considered the obvious explanations first. Could a large planet with an enormous ring system, something like Saturn, but much bigger, be responsible? The data didn't fit. A ringed planet might cause a complex light curve, but it would still repeat on a regular schedule. KIC 8462852's dimming was chaotic. Could it be a swarm of comets, perhaps disturbed by a passing star, sending long trails of dust across our line of sight? The comet hypothesis became the team's leading natural explanation. A family of giant comets could, in theory, produce irregular dimming events. but the scale was staggering. It would require hundreds of comets, each several kilometers wide, passing in just the right way. It was possible, but it felt like a stretch. As Boyajian prepared the team's research paper, they knew the comet idea would not satisfy everyone. Astronomy thrives on healthy skepticism, and this case invited it in abundance. Still, the team needed a working hypothesis, and the comet swarm fit the data better than anything else they could find at the time. In 2015, their paper was published in the monthly notices of the Royal Astronomical Society. It described the discovery, the unusual light curves, and the possible explanations, with comets as the most plausible but far from proven scenario. It also noted that the star showed no signs of infrared excess. If a large amount of dust was blocking its light, some of that dust should be heated by the star and emit infrared radiation. The absence of this signal made the puzzle even stranger. The story might stay within the scientific community if not for what happened next. Jason Wright, an astronomer at Penn State University, read the paper and realized the data resembled something he had studied in a different context: large artificial structures in space. In the realm of speculative science, some had theorized that an advanced civilization might build a vast array of solar collectors around its star, a Dyson swarm, to capture energy on an immense scale. Such a structure could cause irregular, deep dimming events if observed from the right angle. Jason was careful to say this was extremely unlikely. Natural explanations should be exhausted first. But in science, even the improbable must be considered when the data refuses to conform. And here was a star behaving in a way that no known natural process could easily explain. When journalists caught wind of this angle, the story exploded. Headlines proclaimed it the alien megastructure star. Social media lit up with speculation. For many, it was the first time they had heard of Tabby's star, and they remembered it not as KIC 8462852, but as the star that might, just might, be home to a super-advanced civilization. For Boyajian, the sudden attention was exciting and overwhelming. The data was fascinating enough without alien speculation, and she knew how easily that could overshadow the real science. But she also understood that the public's imagination was now engaged, and that interest could help fund the further observations needed to solve the mystery. The media frenzy brought both challenges and opportunities. On the one hand, the alien hypothesis could be a distraction. On the other, it brought resources. In 2016, Boyajian launched a Kickstarter campaign to fund ground-based observations of the star. Thousands of people donated, eager to be part of the search for answers. The campaign succeeded, and for the first time, the star could be monitored continuously from Earth by a dedicated network of telescopes. This was crucial because Kepler's original mission had ended. It had been designed to stare at the same part of the sky for 4 years, but after 2 reaction wheels failed, the telescope could no longer hold its steady gaze in its original configuration. Without new eyes on the star, future dimming events might go unnoticed. The citizen science connection remained central to the story. It was not a high-powered NASA team that first spotted the anomaly. It was volunteers, ordinary people with no formal training, just the patience to scroll through thousands of light curves and the curiosity to flag something unusual. In a sense, Tabby's star became a triumph of open science, a reminder that the universe still has surprises for those willing to look. And so, the world had a mystery, a star that dimmed in ways no one could explain, a team of scientists determined to find the cause, and a public eager to know if the answer might be natural or something far more extraordinary. What they would find in the years to come would deepen the puzzle, challenge the comet theory, and reveal that this strange star was not finished surprising us.
When the story of KIC 8462852 began to spread, it quickly grew from an obscure astronomical finding into one of the most intriguing cosmic mysteries of the decade.
Astronomers, science writers, curious amateurs, and ordinary people all wanted to know the same thing. What could cause a star to flicker so strangely? The first rule of science is to rule out the ordinary before turning to the extraordinary. And so the investigation began, not with wild theories, but with careful, methodical tests. The first possibility was that the signal itself was not real. Kepler was an incredibly precise telescope, but no instrument is flawless. Sometimes what looks like a strange cosmic phenomenon is really just a quirk in the data or a technical error. Could the deep dips in brightness simply be a glitch in Kepler's detectors or its software? To find out, scientists compared KIC 846-2852's data with nearby stars observed at the same time. If it was a detector problem, those stars should show the same strange pattern. They didn't. Their light curves were perfectly normal. The team then went back to the raw data, untouched by software corrections, and saw that the dips were still there. This was not a mistake. Something real was happening to Tabby's star. With instrumental error unlikely, the next suspect was the most common cause of brightness dips: planets. This is what Kepler was built to find. A planet crossing in front of a star will cause a small, predictable dip in brightness. Thousands of planets have been discovered this way. At first, maybe this was an unusually large planet, perhaps a gas giant many times the size of Jupiter. But even the biggest planet in the universe would block only a fraction of the light seen here. The dips in Tabby's star were up to 20%, far larger than any planet could manage. And planetary transits are regular. They repeat with clockwork precision. The dips in Tabby's star were anything but regular. This could not be explained by a planet alone. Some wondered if perhaps a planet with an enormous ring system could be the answer, something like Saturn's rings, but far more massive, tilted in just the right way to create an unusual light pattern. Rings can cause complicated, layered dips in brightness, but the same problem emerged. The pattern would still repeat each orbit, and Tabby's star's dips were unpredictable. This idea, too, had to be set aside. The next hypothesis was one Boyagin's team had already considered in their paper: a swarm of comets. Imagine hundreds or thousands of icy bodies, each with long trailing tails of dust, streaming past the star in quick succession. Such a swarm could block varying amounts of light, creating a jagged, irregular light curve. Cometary dust could explain why the dips were sometimes asymmetric, why the light faded more slowly than it returned, or vice versa. But there were serious issues. The number of comets needed was staggering, far beyond what even a busy star system might normally contain. And all that dust would absorb the star's heat and glow faintly in infrared light. Yet, infrared observations revealed no such glow. It was possible, yes, but it required stretching the limits of plausibility. Dust, in general, was the next line of thought. Dust between us and the star could dim its light, especially if the grains were large enough. Dust clouds can be irregular, creating inconsistent dips. If the dust was in interstellar space, somewhere between us and Tabby's star, it might not produce a detectable infrared signal. But then other nearby stars should dim in the same way, and they didn't. If the dust was orbiting the star itself, it would be warmed and would glow in infrared, which, again, was not seen. Dust wasn't ruled out entirely, but it failed to explain the whole picture. Then came a more violent idea. Perhaps two planets had collided in Tabby's star's system, shattering into vast clouds of debris. Such an impact could produce the massive, uneven dips we saw, at least for a while. Our own moon, scientists believe, was formed after such a collision. But here again, infrared data became the obstacle. Fresh debris should glow for centuries, yet Tabby's star showed no infrared excess. If such a collision had occurred, it would have had to happen long enough for the debris to cool, and long enough for the fragments to settle into regular orbits. But the dips we saw were still chaotic. And then there was the idea that refused to stay in the background, the one that grabbed the public's attention more than any other. What if we were seeing something built by an alien civilization? This was not idle fantasy. It came from a concept first proposed by physicist Freeman Dyson in the 1960s. A sufficiently advanced society might build vast solar collectors around their star to harvest its energy, a Dyson sphere or Dyson swarm. Such megastructures would block a star's light in irregular, unnatural ways. Jason Wright, an astronomer at Penn State, had suggested this as a distant possibility, a last resort to consider only if all other explanations failed. The odds of catching such a thing in progress were vanishingly small. And yet, the data was undeniably odd. When the media caught wind of the alien megastructure idea, headlines exploded with speculation. Talk shows debated the possibility of first contact. Scientists were more cautious. This was an extraordinary claim, and extraordinary claims require extraordinary evidence. The Search for Extraterrestrial Intelligence, or SETI, turned its radio telescopes towards Tabby's star, listening for any artificial signals. For weeks they listened. The result was silence. No beacons, no transmissions, nothing that could be called a message. Silence doesn't prove there's nothing there, of course. It only tells us that if someone is there, they're not broadcasting in a way we can detect. By early 2016, the list of possible explanations was long, but none felt entirely satisfying. Instrument problems were ruled out, planets and rings couldn't account for the irregularity or the depth of the dips. Comets were possible, but improbable. Dust had issues with the color and infrared data. Collisions didn't match the cooling time. And aliens, well, they remained the most exciting but least supported option. The only way to move forward was to gather more data. Thanks to a wildly successful Kickstarter campaign led by Boyajian herself, a network of ground-based telescopes was set up to watch the star constantly. If it dimmed again, scientists could point other instruments at it immediately. This was key because the color of the light during a dip would be a powerful clue. Dust blocks blue light more than red, so if the dips were dust-related, the star would appear slightly redder. A solid object, whether natural or artificial, would dim the star evenly across all wavelengths. This kind of rapid response could finally separate one theory from another.
Months passed. For a while, Tabby's star seemed calm, as if nothing unusual had ever happened. Astronomers waited, telescopes ready, knowing the star could change at any time. Patience is a strange thing in science. It feels passive, but in reality, it's a coiled spring. Every night of quiet skies brought us closer to the moment we've been waiting for. Then, in May 2017, the waiting ended. Without warning, the star began to fade again. Not a sudden blackout, but a slow, steady dimming, like someone was drawing a sheer curtain across its light. News traveled quickly through the astronomy network. Observers from California to Spain received alerts. Lenses turned, sensors aligned, and Tabby's star was once again the focus of intense scrutiny. This time was different. We weren't relying on old data. We were watching in real time with the fleet of instruments capable of measuring not just brightness, but the exact color of the light as it changed. Day by day, the dip grew deeper. Astronomers began assigning names to each event, Elsie, Celeste, and so on, both to humanize them and to keep the records organized. Elsie, the first dip of 2017, dropped the star's light by about 2%. It was smaller than the massive dips seen by Kepler years earlier, but still far larger than the changes most stars ever show. As Elsie unfolded, the key measurement came in. The light was indeed changing color. Blue light was dimming more than red light. This was the signature of dust. Not large objects, not alien megastructures, but fine particles scattered in space. Dust grains small enough to scatter shorter wavelengths more effectively than longer ones. This was a turning point. It didn't solve the mystery, but it narrowed the field. Over the next few months, more dips came. Elsie followed Elsie, then two more events nicknamed Skara Brae and Angkor. Each one had a slightly different shape, depth, and duration, and each one showed the same pattern, more blue light blocked than red. This consistency strengthened the dust theory, but left a nagging question: where exactly was the dust coming from? If the dust were in interstellar space between us and the star, it would have to be part of a cloud so oddly shaped that dimmed only this one star and none of its neighbors. That seemed unlikely. If the dust were orbiting Tabby's star, it would have to survive very close to a hot, luminous sun without being blown away by stellar winds. Dust is fragile. In the inner regions of a solar system, it tends to either spiral into the star or be pushed out entirely. For the dust to keep appearing, something had to be replenishing it constantly.
One possibility was ongoing collisions, perhaps a steady rain of asteroids smashing into each other, creating plumes of fine material. Another was that the dust came from the tails of comets or icy fragments vaporizing as they passed close to the star. The trouble was scale. The dips were irregular, both in depth and timing. Whatever was creating the dust wasn't on a single neat orbit. It was chaotic, messy, unpredictable. Meanwhile, the long-term data brought another layer of mystery. Astronomer Ben Montet and graduate student Joshua Simon had gone back through Kepler's full data set and found something unexpected. Over the 4 years Kepler watched the star, it didn't just suffer sudden dips, it also faded steadily overall by about 3%. That's an enormous change for a star in such a short time. And when they compared ground-based photographic plates from decades earlier, they found evidence the star might have been dimming for a century. No known stellar process produces this combination of short, sharp dips and a slow, steady fade. It was as if we were looking at two mysteries at once, a short-term phenomenon layered on top of a long-term trend. The dust could explain the short-term events, but the century-long fade, that was harder. If the fade was real, and there's still debate about that, it would require a truly colossal amount of material to block that much light over such a timescale. Some researchers began to suggest more exotic scenarios. Maybe we were witnessing the breakup of an entire planet, slowly crumbling into dust under the star's gravity. If the planet was icy, like a giant comet, it could produce clouds of fine particles with each pass. Over time, it would disintegrate completely, explaining both the dips and the fading. Another idea was that we were seeing the remnants of a massive moon torn apart by tidal forces and its pieces now orbiting in a chaotic swarm. Others proposed that Tabby's star itself might be doing something unusual internally. Stars can have cycles and instabilities that change their output, though none known to science match this exact pattern. Could it be undergoing a slow transformation, perhaps on its way to becoming a different type of star? That would make it a rare and valuable find, but the lack of similar cases left the idea without strong support. And still, in the background, the alien hypothesis persisted. The color data argued against large, solid structures blocking the light, but supporters noted that even an advanced civilization's projects could be messy. Perhaps what we were seeing was the demolition of something vast, scattering debris and dust. Or perhaps the megastructures themselves were partially damaged, their pieces now drifting into space. It was speculative, and the majority of astronomers leaned toward natural causes. But the mystery's strangeness kept the thought alive in the public imagination. By late 2017, the flurry of new dips had slowed, and the star returned to relative calm. But the monitoring network remained in place, ready for the next event. This constant watch had changed the way astronomers study such anomalies. Instead of relying on whatever data happened to be available, we now had a coordinated system capable of jumping into action at the first sign of change. This meant that the next time something strange happened in our galaxy, we could respond immediately. Tabby Boyanji herself became an icon of persistence in science. The star bore her name in everyday conversation, something almost unheard of for a living scientist. Her willingness to embrace uncertainty, to admit when the answers weren't there yet, inspired both professionals and amateurs. In interviews, she would often say that the real story wasn't just the star, it was the process. Science at its best isn't about confirming what we already believe. It's about following the evidence, wherever it leads, even if it takes years, even if it means discarding our favorite ideas. Meanwhile, people around the world found themselves oddly attached to a star they couldn't even see without a telescope. It became a kind of cosmic character, unpredictable, moody, and endlessly fascinating. Every new dip was like a plot twist in an ongoing drama. Forums lit up with speculation. Artists painted what alien megastructures might look like. Writers imagined civilizations living in the shadows of massive light collectors. The mystery had crossed from science into culture. And then came an unexpected twist.
a reminder that mysteries don't always resolve the way we expect. In 2018 and 2019, fresh dips occurred. Once again, dust was the likely culprit, based on the way the light changed color. But this time, the patterns hinted at something new: the possibility that multiple sources of dust, at different distances from the star, were acting at once. This could mean we were looking at a complex system in the middle of some grand upheaval, perhaps the late stages of planet formation or the chaotic aftermath of destruction. The truth is, we still don't have a final answer. Tabby star has taught us that nature can outwit even our best theories, that sometimes the universe writes stories stranger than fiction. The investigation continues. New telescopes, more powerful than Kepler ever was, are now joining the watch. Instruments like the James Webb Telescope can study the star's light in exquisite detail, searching for the chemical fingerprints of the dust. Maybe, in the near future, we'll catch it in a dip and finally see exactly what it's made of. Until then, we keep watching, because somewhere out there, nearly 1,500 light-years away, a star is flickering in a way no other star we know does. And in that flicker, in that strange and stubborn dance of light, is a reminder of why we look up at all. Not just to find answers, but to find better questions.
For most scientists, the alien megastructure theory was always the least likely. The odds were stacked against it. History had shown, time and again, that strange astronomical events usually had natural explanations. Pulsars were once called LGM, little green men, because their perfect radio pulses seemed artificial. Quasars, too, were briefly suspected of being technological beacons. In both cases, deeper study revealed them to be fascinating but purely natural phenomena. The lesson seemed clear. Nature is weird enough without invoking extraterrestrials. And yet, Tabby's star refused to fit neatly into any known category. That's what made the alien idea so stubborn. Not that it was probable, but that it was so hard to rule out entirely. Even a sliver of possibility was enough to keep imaginations alive. So for a moment, let's lean into the what if. Not as proof, not as a claim, but as an exploration of what it would mean if the flickering light of KIC 8462852 was indeed the shadow of something built by intelligence. The most famous version of this concept is the Dyson sphere, or more accurately, a Dyson swarm, a vast collection of energy-collecting satellites orbiting a star. Proposed by physicist Freeman Dyson in 1960, the idea was simple but bold. If a civilization grew advanced enough, it would need more energy than any planet could provide. The logical next step would be to tap directly into its star's output, capturing a significant fraction of its light for power. In its complete form, a Dyson sphere would completely enclose a star, blocking its light entirely from the outside. But a partial version, a loose swarm of collectors, would let some light through, perhaps in irregular patterns. If these structures were moving, growing, or being dismantled, they could cause strange, unpredictable dips in brightness. In the case of Tabby's star, the irregular dips could, in theory, be explained by large, uneven swarms of such objects passing in front of the star from our point of view. The century-long dimming could be the result of more and more of these collectors being added over time, gradually obscuring more light. In this scenario, we might be witnessing an alien construction project in progress. It's a compelling image. Somewhere, far beyond our reach, an advanced species has decided to reshape its solar system to suit its needs. Massive structures, each larger than entire planets, gliding silently through space. From our perspective, 1,500 light-years away, all we see is the faint flicker of their silhouettes. But if this were the case, we might expect other clues. For instance, a Dyson swarm would not only block light, it would also re-radiate energy as heat in the infrared spectrum. Astronomers have searched for such excess infrared radiation from Tabby's star and found little to none. This is one of the strongest arguments against the megastructure hypothesis. Without that heat signature, it's harder to imagine vast artificial collectors being responsible. Unless, of course, the builders were using the energy in a way that minimized waste heat or radiated it in wavelengths we're not looking for. Some have taken the speculation further. Perhaps what we're seeing isn't construction, but destruction, the dismantling of an existing structure, the debris drifting into chaotic orbits. Or perhaps the star is being mined directly, its material harvested in a way that creates dust and blocks light. These are imaginative ideas, but they demand extraordinary evidence we don't yet have. Still, the alien angle has value, even without proof. It forces us to think bigger, to consider possibilities beyond our current experience. In doing so, it pushes the boundaries of what we look for and how we look for it. In the years since Tabby's star became famous, the search for extraterrestrial intelligence has expanded to include not just radio signals, but also unusual patterns of light, strange chemical signatures in exoplanet atmospheres, and other indirect clues. And there's a deeper, more personal effect. When people hear about the possibility, however slim, that we might be witnessing alien engineering, they feel a sense of connection to the cosmos. It's no longer just distant gas and dust, it's potentially a stage where another intelligence is at work. It transforms the universe from a cold, indifferent expanse into something alive with potential meaning. For the scientists involved, keeping this idea in the mix, even as an unlikely outlier, is a delicate balance. They must remain rigorous, favoring explanations that fit the evidence. But they also understand the power of mystery. Public interest in Tabby's star brought funding, attention, and a wave of citizen science participation. Without that excitement, the intensive monitoring campaigns that revealed so much about the star might never have happened. This tension between skepticism and wonder is part of what makes science human. We yearn for extraordinary discoveries, but we're also bound by the discipline of proof. The alien hypothesis may never move beyond speculation for Tabby's star, but it's a reminder of why we look at the sky in the first place, to see not just what's there, but what might be. In the end, whether Tabby's star is the work of nature or something else, it occupies a rare space in our collective imagination. It sits at the crossroads of astronomy and possibility, a flickering point of light that invites both careful measurement and wild dreaming. And perhaps that's the most lasting gift it's given us, because when we ask, could it be aliens, we're also asking something more personal. Are we alone? And even if the answer here is no, even if Tabby's star turns out to be nothing more than dust and debris, the act of asking keeps the door open for the day we finally find a yes.
If the alien megastructure theory sits at one extreme of the imagination, the other end is grounded in the dust and grit of astrophysics. And here, in the realm of the ordinary, scientists believe we may find the real answer to the mystery of Tabby's star. From the earliest observations, one idea kept returning. Maybe the light wasn't being blocked by massive, solid objects at all. Maybe it was something far smaller, more diffuse, and far more common in the universe: dust. On the surface, dust might sound anticlimactic. After all, cosmic dust is everywhere, drifting between planets, stars, and galaxies. But dust is also powerful. In the right amounts and configurations, it can hide entire stars from view, sculpt the glow of nebulae, and shift the very color of light we see. The first question scientists asked was simple. If dust was responsible for Tabby's star's flickers, what kind of dust could do it? Ordinary interstellar dust tends to block light in predictable ways, dimming stars more in blue light than in red. But the dips in Tabby's star's brightness weren't entirely consistent with that pattern. Sometimes the star dimmed more evenly across the spectrum. Sometimes the effect varied from one dip to another. The search for answers led researchers to consider other kinds of dust, perhaps dust orbiting the star itself rather than drifting randomly through space. Dust produced by the breakup of comets, for example, could be clumpy and uneven, creating unpredictable shadows. A single large comet would be too small to cause a deep dip, but a whole family of them, breaking apart in sequence, might produce exactly the strange pattern we were seeing.
Another theory suggested the star might be consuming or breaking apart a planet. In this scenario, gravitational forces or stellar activity could rip material from the planet's surface, turning it into a cloud of fine debris. This debris would swirl around the star, gradually spreading and drifting, blocking light in irregular bursts. The century-long dimming could be the result of a slow but steady increase in the amount of this debris. One of the most compelling pieces of evidence for a dust-based explanation came from infrared observations. When dust absorbs light, it heats up and re-emits that energy as infrared radiation. If large solid objects were blocking the light, we wouldn't expect much of an infrared signal. But if dust was responsible, there might be a faint excess in the infrared spectrum. Observations did show hints of such an excess, though not enough to fully settle the debate. Even the nature of the dust itself became a subject of investigation. Could it be unusually large grains that block light differently than normal interstellar particles? Could it be made of exotic minerals, capable of surviving closer to the star without vaporizing? These questions remain open, each possibility adding another layer to the mystery. What makes the dust theory appealing is that it fits into patterns we've seen elsewhere. Stars with debris disks, comet swarms, or planetary collisions often show variability in brightness. The processes that create that variability, impacts, breakups, and evaporation, are messy and chaotic, capable of producing the kind of irregular light curves we see in Tabby's star. But the dust idea has its own challenges. For one, the sheer amount of dust required to cause the deepest dips is enormous. Keeping that much material in the right place for so long, without it dissipating or falling into the star, is difficult. And if the dust is orbiting the star, it should eventually spread out evenly, reducing the irregularity of the light dips. Yet Tabby's star's behavior remains stubbornly erratic. To address these problems, some researchers have proposed hybrid models. Perhaps the star is experiencing bursts of activity that periodically produce fresh dust, keeping the pattern chaotic. Or maybe large fragments of broken-up bodies are contributing alongside the fine dust, creating a mixture of deep and shallow dips. The comet swarm idea in particular has its advocates. Comets are rich in dust and gas, and they can survive long orbits before breaking apart near a star. A carefully timed cascade of cometary destruction could, in theory, mimic the strange light curve we've observed. Still, even among scientists who favor the dust hypothesis, there is no single universally accepted model. Each version of the idea explains some observations well, but struggles with others. It's a reminder that in astronomy, as in life, the simplest answer is not always easy to prove. And yet, dust has a certain beauty as an explanation. It strips away the grandeur of megastructures and alien civilizations and leaves us with a cosmic truth. The universe is built not just from massive stars and planets, but also from the smallest particles, drifting silently across gulfs of space. These tiny fragments can, from thousands of light years away, change the way an entire star appears to us. In this sense, dust is not a disappointment. It is a storyteller, capable of shaping the light of a star into patterns that puzzle even our most powerful telescopes. Whether or not it holds the answer to Tabby's star, it reminds us that the universe's mysteries often emerge from the humblest materials. And so, the dust theory stands, not as the final word, but as one of the strongest contenders in the ongoing debate. If it's true, the strange flicker of Tabby's star may be nothing more than the cosmic equivalent of a dusty window, briefly clouding our view. But if it's not, then we are still in the presence of something far rarer, waiting to be uncovered.
If Tabby's star were alone in its strangeness, it might be tempting to think it was a singular cosmic accident, a one-off quark in an otherwise orderly sky. But it is not entirely alone. The universe holds other stars whose light curves defy easy explanation, and by studying them, we can begin to place Tabby's star in a wider context. One of the most famous examples is known as RZ Piscium. Located in the constellation Pisces, it is often nicknamed the Death Star, not because it destroys planets with lasers,
but because it appears to be in the process of consuming one. Its light dims dramatically and unpredictably, much like Tabby's star. Astronomers suspect it is surrounded by clouds of debris, possibly the remains of a shattered planet, which periodically block the light. If true, RZ Piscium could be a snapshot of planetary destruction in progress. Another case is EPIC 204-278-916, a young star observed by NASA's K2 mission. Over an 80-day period, this star's brightness dropped by up to 65%, far more than Tabby's star ever has, and the dimming lasted for weeks at a time. The leading theory is that massive clumps of dust or gas, possibly linked to the early stages of planet formation, were orbiting close to the star. In this sense, EPIC 204-278-916 might be showing us the chaotic birth pangs of a new solar system. Then there is VVV-WIT-07, a star in the direction of the galactic bulge that dimmed by 80% and then returned to normal, as if something enormous and opaque had passed directly in front of it. The dimming lasted several months, too slow for a typical planetary transit. One idea is that an unseen companion star with a vast ring system larger than Saturn's by many orders of magnitude may have eclipsed it. These examples serve as reminders. Stars are not the steady, unchanging lights we often imagine. They live in dynamic environments filled with dust, planets, comets, and sometimes other stars. Each of these companions can leave its fingerprint on the light we see. And yet, none of these stars behave exactly like Tabby's star. RZ Piscium's variability seems tied to a violent planetary demise. EPIC 204-278-916's dips are longer and likely caused by youthful instability. VVV-WIT-07's eclipse was a single, extraordinary event, not a recurring puzzle. Tabby's star is unique in the irregularity and variety of its dimming, sometimes shallow, sometimes deep, with no fixed period, and accompanied by a century-long fade. In searching for analogs, astronomers also turn to binary systems, where one star's light can be altered by its companion. In some cases, a small, faint star can pass in front of its brighter partner, causing dips that mimic planetary transits. But such systems usually leave telltale signs in the spectrum of the starlight, and Tabby's star shows no such evidence. The hunt for similar light curves is ongoing. Large-scale sky surveys like the Zwicky Transient Facility and the upcoming Veracruz Rubin Observatory's Legacy Survey of Space and Time will monitor billions of stars, looking for any that share Tabby's star's peculiar behavior. Finding even one close match could help unlock the mystery. If we saw a second star with the same kind of erratic dimming, we could compare environments, ages, and surroundings, perhaps revealing the underlying cause. But there's a catch. The universe is vast and anomalies are rare. Even with our most ambitious surveys, the odds of finding another Tabby are low. Not zero, but low. This rarity is part of what keeps the star so captivating. It stands as an outlier, a cosmic signature we cannot yet read. The search for other weird stars also has a philosophical dimension. It forces us to consider how much of what we see in the night sky is filtered through our own assumptions about what is normal. For centuries, we imagined stars as perfect, eternal points of light. Then we learned they are born, live, and die in spectacular ways. Now, with discoveries like Tabby's star, we are reminded that even in the middle of their lifetimes, stars can surprise us, behaving in ways that stretch the limits of our theories. Each unusual star is a challenge, a reminder that the universe does not bend to fit our models. Sometimes, the models most bend to fit the universe. Tabby's star may be the most puzzling of these objects, but it is not the only one whispering that our understanding is incomplete. It belongs to a small but growing family of cosmic mysteries, each one a piece of a puzzle too big to see in its entirety. And in this family, Tabby's star remains the enigma among enigmas. The others give us hints, parallels, and contrasts, but none can fully explain it away. This leaves us where all great mysteries leave us,
on the edge of the known, looking out into the dark, wondering what waits to be found.
Science is often portrayed as a realm of pure logic, a place where facts are gathered, theories are tested, and conclusions are drawn without bias or emotion. But the story of Tabby's star is as much a human drama as it is an astrophysical puzzle. Behind every data point is a person. Behind every theory, a mind shaped by curiosity, ambition, and sometimes doubt. It begins with the moment of discovery. Tabitha Boyajian, the astronomer who first brought the star to the world's attention, remembers looking at the Kepler data and seeing something she could not explain. This was not just a minor statistical blip, it was a glaring, undeniable anomaly, a pattern that broke the expected rules. That kind of moment can be exhilarating, but it is also isolating. When you find something that doesn't fit, you are faced with two possibilities. Either the data is wrong, or the universe is stranger than you thought. Her team checked the data again and again, ruling out glitches, calibration errors, and instrument problems. The signal held. The dips were real. Only then did the emotional weight of the discovery start to set in. They were staring at something unprecedented, and with that realization came a flood of questions. In the early days, the scientific community's reaction was mixed. Some researchers were immediately intrigued, eager to join the investigation. Others were skeptical, suggesting the dimming might be due to something mundane, a passing cloud of dust, a background star, or a misinterpretation of the data. Skepticism is healthy in science, but it can also sting. When you've put your professional credibility on the line, hearing others dismiss your work as a mistake is not easy. Still, Boyajian and her colleagues pressed forward. They wrote papers, gave talks, and invited others to test their ideas. And that openness paid off. A team at Penn State, for example, analyzed archival photographic plates spanning a century and found evidence of a slow, long-term dimming. That data point, surprising and still debated, added another layer to the mystery. As the story spread beyond academic circles, the public began to take notice. News outlets seized on the most sensational possibility, the idea that the dimming might be caused by a giant alien structure. Suddenly, the scientists found themselves fielding calls from journalists, radio hosts, and even late-night talk show producers. For some researchers, this was thrilling. For others, it was deeply uncomfortable. The fear was that the alien angle would overshadow the careful, methodical science. Yet the public attention brought unexpected benefits. When Boyajian launched a crowdfunding campaign to fund further observations, thousands of people contributed. It was one of the largest citizen-funded astronomy projects in history, and it allowed continuous monitoring of the star through the Las Cumbres Observatory Network. In this way, the mystery became a shared endeavor, a collaboration between professional scientists and an engaged, curious public. But the debates within the scientific community remained sharp. Some astronomers argued for natural explanations, pointing to new data suggesting the dips were more pronounced in blue light than in red, consistent with dust. Others countered that the pattern and timescale of the dimming still defied conventional dust models. Every conference presentation sparked new rounds of discussion, sometimes heated, as researchers argued over the implications. Through it all, there was a sense of humility. Even the most confident scientists admitted in quieter moments that they did not have a definitive answer. And that is not an easy thing to say in a field that prizes solutions and certainty. For some, the frustration was palpable. For others, it was a source of motivation, a reminder that discovery often begins with not knowing. In the emotional journey of the Tabby Star team mirrors the way many great scientific mysteries unfold. There's the rush of discovery, the weight of skepticism, the thrill of public engagement, the grind of data collection, and the stubborn persistence required to keep searching when the answer remains elusive. It's a story of persistence, not just in the face of the unknown, but in the face of doubt, from others and from oneself. In the end, the people studying Tabby Star are not chasing fame or headlines. They are chasing understanding. They know that even if the mystery turns out to have a simple explanation, The path to that explanation will have expanded our knowledge, sharpened our tools, and prepared us for the next anomaly the universe throws our way. Science is not a straight road. It is a twisting path through terrain we do not fully understand. And sometimes, it is the questions with no clear answers that keep us moving forward.
The universe is vast. So vast that even our most ambitious metaphors barely touch the truth. Every star we see is just one pinprick of light in a cosmic ocean, and every one of those stars may hold its own secrets. Tabby's star is one of those secrets. And perhaps it is a reminder that the universe does not owe us clarity. We are a young species. Our telescopes have been looking at the stars for only a few centuries. Our detectors, our sensors, our methods, they are works in progress. We are explorers peering through a keyhole, trying to describe an entire landscape. And every so often, we see something through that keyhole that does not fit the map we have drawn. The dimming of Tabby's star may one day be explained in neat scientific terms. It might turn out to be a kind of dust we have never fully cataloged. It might be the debris of a shattered planet drifting in irregular clouds across our line of sight. It might be something so ordinary, once revealed, that we wonder how it ever seemed extraordinary. Or perhaps it is something else. Perhaps it is the faint signature of engineering on a scale we can barely imagine. Perhaps it is the shadow of a civilization that learned to harness the power of its sun. Perhaps it is a sign that the universe is not silent, only subtle. Whatever the answer, the search itself matters. Science is not just about collecting facts. It is about stretching the boundaries of what we think is possible. It is about being willing to follow a question into the dark, even when there is no guarantee of light at the end. For the people studying Tabby's star, the journey is far from over. Observations continue. Theories evolve. Data builds, one measurement at a time. And with each year that passes, our instruments grow sharper, our perspective wider. One day, perhaps soon, perhaps decades from now, the mystery of this impossible star will be solved. And when it is, it will become another story in the long history of human curiosity. A story of how we looked at the sky and saw something we could not explain and refused to stop looking until we understood. But even then, there will be other mysteries, other stars, other strange lights flickering in the dark. The universe will not run out of questions, and we will not run out of reasons to keep asking. Because in the end, this is what it means to be human. To stand on a tiny world orbiting an ordinary star and still believe it is worth asking what lies beyond. To look into the night sky and see not just beauty, but possibility. Tabby's star is still out there, 1,480 light-years away, quietly shining and dimming in patterns we do not yet understand. It does not care that we are watching. It does not care about our theories or wonder. And yet, in its indifference, it has given us a gift, a reason to look deeper, think harder, and dream bigger. The star that should not exist, exists. And for now, that is enough.
There is something strange that happens after you spend enough time with a mystery like Tabby's star. At first, it feels distant, a scientific puzzle far away in space and time. But slowly, as you keep returning to it, the mystery begins to feel personal. You start to wonder not just what it is, but why we found it at all. Out of the hundreds of billions of stars in our galaxy, why this one? Why now, in this narrow sliver of human history with our still primitive instruments? The odds seem almost absurd. It is as if the universe placed a small knot in the fabric of the sky and dared us to untangle it. That is the quiet truth of astronomy. It is not just about finding things, it is about finding ourselves in the act of searching. Every observation is a mirror, reflecting not only the cosmos, but our own place within it. Perhaps Tabby's star is a reminder that discovery is not a straight road from question to answer. It is a winding trail with detours, dead ends, and sudden openings to new vistas. Sometimes the trail loops back on itself, and you realize you're asking the same questions you began with, only now they mean more. There is a tendency in science and in life to want closure, to wrap the mystery in a neat box and put it on a shelf. But not all mysteries are meant to end quickly. Some exist to stretch across decades, generations even. They become milestones for future scientists, markers along humanity's slow, steady march into the unknown. And so, Tabby's star waits, not impatiently, not urgently, just existing in its strange rhythm, its light flickering across the gulf of space to reach us. Every photon is a traveler, born in the star's blazing heart, crossing nearly 15 centuries before ending its journey in the glass of our telescopes. When we study those photons, we are reading ancient messages sent long before humans built cities or even wrote words. If there is a civilization around Tabby's star, we may never meet them. If there is none, then the star's mystery is still no less profound, because either way, it has given us something rare, a challenge to our understanding of how the universe works. And maybe that's the most important part, not the final answer, but the act of questioning, not the resolution, but the journey we take to seek it. The story of Tabby's star is still being written. Some future telescope orbiting far beyond Earth may one day collect the data that makes everything clear. When that happens, our understanding will change, but the wonder, the awe, will remain. Because in the grand arc of the cosmos, the star that should not exist is not an ending, it is a beginning.
There is one possibility we have not yet spoken aloud. It is not the most probable, it is not the most comfortable, but it is the one that lingers at the edge of the mind when the lights go out and the night sky stretches above you. What if we are not simply observers of Tabby's star? What if, in some way, we are participants? We look up and see light that left its home nearly 1,500 years ago. If there is intelligence around that star, they may be looking back at light from our own sun, light from our Middle Ages, when our world was still a patchwork of kingdoms, and the idea of flight, electricity, or space travel was unimaginable. Perhaps, for them, we are the strange flicker and the dark. It is tempting to think of alien contact as a sudden, dramatic event, a message beamed across space, a ship descending into Earth's atmosphere. But maybe the first contact is far quieter. Maybe it is the shared act of noticing each other's stars and realizing that both sides are asking the same question: who else is out there? And here is where the thought grows unsettling. If they are watching, they have been watching for a very long time, long enough to see our world transform from scattered settlements to a planet laced with lights, signals, and satellites. If they are listening, they have already heard the first whispers of our radio transmissions, faint but distinct against the cosmic background. They would know we are here. Of course, it could all be coincidence, a quirk of dust, a debris field,
a natural phenomenon with no mind behind it. But even that possibility carries its own quiet weight. Because if this mystery is not about them, then it is entirely about us, about our hunger to explain the unexplainable, about our willingness to imagine more than what we can prove. In the end, Tabby's star may never give us the story we want, but it has already given us something else, a reason to lift our eyes and think in terms of centuries, millennia, and light years. It has reminded us that in the vast, cold silence of space, the greatest noise is our own curiosity. So perhaps the star is not a message at all. Perhaps it is a mirror, and what we see reflected in it is not them. It is ourselves, standing on the edge of the cosmic ocean, daring to believe we are not alone.